So today we are going to go over 8.7 part 1, Taylor and Maclaurin polynomials and approximation. So in the first part of chapter 8, we went over the convergence and divergence of a series. But where we can use series, this lesson will give us an idea. How do we use series to approximate any function? Let's have a look at the do now problem. Find the equation for the tangent line approximation for the function, quadratic function here. So given a parabola, we can use a line to approximate. However, a line might not be accurate if we go approximate a value far away from the given point. What's a better way? In this lesson, we can use another series to approximate, which will give us more accurate answers. How to do the line approximation? So first, we find the slope. So the slope will be the derivative at x equals 1. The function derivative is 2x minus 4. X equals 1 give us negative 2. So now we have to find the point. When x equals 1, we plug 1 in. 1 minus 4 plus 3 give us 0. So the equation of the tangent line will be y minus 0 equals negative 2, x minus 1. So y equals negative 2x plus 2. So this is the tangent line at 1. So we can use this line to approximate, for example, the function value at 1.1 will be approximately given by the line, which is negative 2.2 plus 2, negative 0.2. However, as I said, this can only approximate very close to 1. If we want to approximate, for example, x equals 2, that error will be huge. So in this lesson, we are going to show you another polynomial approximation, which we call Taylor and Maclaurin polynomial. So this is used to approximate any function at any given point C. The nth term of Taylor polynomial centered at C is given by the nth term we call it Pn of x, which is f of c plus the derivative. The first derivative, x minus c, plus second derivative over 2 factorial, x minus c squared. These are all 2's. And keep going until nth derivative over n factorial times x minus c to the nth power. Keep in mind, c is our center, which is a constant here. And if the special case, if the center equals 0, the nth polynomial, nth term polynomial will be given by f of 0 plus 0 derivative times x minus c. So you replace all the c's using 0. This is the what we call Maclaurin polynomial approximation. So our goal is trying to approximate function f of x using the nth term polynomial. And of course, when n goes to infinity, they will be equal. Let's have a look at an example. How do we write this out? Find the fourth degree. The fourth degree means we are going to have x to the fourth power. Maclaurin approximation, that means center equals 0. So given for fx equals e to the x, given y equals e to the x, so this is f of x. First, we take the derivative. Take the second derivative. Third power, third derivative, and the fourth derivative. So the polynomial, whenever we solve this type of problem, we want to write the formula down. So f of 0 plus derivative at 0 times x plus So after we write this formula down, the information we need will be f0, zero derivative, second derivative, third derivative, and fourth derivative. So f of 0 is given by e to the 0, which is 1, f0 prime, which is also 1, double prime, triple prime, or the fourth derivative will be all 1. So now we plug everything in. So this is P4 of x is given by f of 0, which is 1, plus x, plus 2 factorial, which is 2, 3 factorial, 6, 24 factorial, 4 factorial, 24. So this means e to the x, if we use the fourth term Maclaurin polynomial, which will be 1 plus x squared over 2 factorial plus. You don't have to simplify it if you don't want to. You can leave it like this. For example, e to the 0, when x equals 0, is approximate 1. E to the first, which is approximately 1 plus 1 plus 1 over 2 plus 1 over 6 plus 1 over 24. So this is just an approximation. And in the future, we are going to learn if we use this to approximate the original function, we are going to have another error bound.